Hello and welcome. This is the Chapter 3 intro video. Chapter 3 is on chemical reactions and reaction stoichiometry. This chapter is about quantifying details within chemical reactions. So doing things like calculating yields of a reaction, how much product do we expect to form, maybe how much of one reactant do you need to react with another reactant. And then we also discuss how you determine formulas from some data that you might find, like percent composition data. You may recall these problems from high school, so we'll talk about how you determine formulas from experimental data within this chapter. As well, we'll talk about the mole, and we'll also introduce a few different types of chemical reactions early on in the chapter. So real basic introduction here to chemical reactions. I think we're probably well aware of writing things like 2H2 plus O2 goes to 2H2O implies that we're taking two hydrogen molecules before the reaction, reacting them with one O2 molecule, and then as a result we're forming two waters. So it's like we're taking the H2, somehow breaking the bond, wedging an oxygen between to make one of the waters, and then doing likewise the same for the other oxygen and the other hydrogen. So we need two hydrogen molecules, one oxygen molecule. When they react fully, they form two water molecules. Okay, now one of the things that we like to have is mass balance. So we like to have the same number of atoms on the reactant side as the product side to know that we have a balanced chemical reaction. So our reactants are really our before, and then the products are the after. Now, one of the things that we'll see is that when we have a balanced reaction, the coefficients are implying how many of each of the molecule we need. The coefficients are referring to how many atoms of each of the elements are present within one unit of that particular molecule or compound. So we see other symbols within chemical reactions. If we look at this reaction here, this is actually a combustion reaction. So any reaction of, say, a hydrocarbon with oxygen forming CO2 and water is an example of a combustion reaction. And so we see here CH4 plus O2 goes to CO2 plus water. So to balance here, we're going to need two water molecules. That gives us four H's on both sides. And then we have two oxygens here, so we need two O2s on the reactant side. So we have four atoms of oxygen on both sides, and then just one carbon on both sides. Okay, so some of the symbols you see here, you see we can get the physical state of the substances. In this case, they're all gases, so gaseous reactants forming gaseous products. You see a delta symbol here. This implies heat. So this implies that we're heating this reaction up or giving it a flame. Usually the delta symbol means you just give it like an instant spark and then it begins to take place. Sometimes you see it used for when you have to continuously heat a reaction. This particular reaction is just like the H2O2 bomb we detonated in class. You just give a little spark and then the reaction goes from there very quickly. We'll pick up in Chapter 5 the nature of the thermodynamics that our reactants turn out in this reaction to be uphill, the products downhill, in terms of their relative energies or what we'll see are enthalpies. So we'll see this discussion come out in Chapter 5. So then the states of matter we can see are things like gas G, liquid L, solid S, really basic. Aqueous we see in Chapter 4 a bit more, but that implies that something's dissolved in water. So if you see AQ, that means dissolved in water. So again, combustion reaction could be any hydrocarbon, in this case C3H8, reacting with oxygen to form CO2. Only difference, we need three CO2s to balance the carbons, four waters to balance the hydrogens, and then we just count up the oxygens from there. 4 plus 3 times 2, so that would be 10. So we need 5 O2 molecules. And then you can picture this. You have two molecules, or excuse me, you would have one molecule of propane reacting with 5 molecules of O2 to form 3 molecules of CO2, 4 molecules of H2O. This is envisioning the CH4 reaction kind of before and after. So this here has two CH4 molecules, some O2. We're forming CO2 and water. Here we're going to get two CO2s from the two carbons in the CH4s. That's going to take one molecule of O2 each. So you can kind of imagine lassoing out these atoms. We've lost the oxygens here, and then we're going to pair up and form water molecules. So we have 4 H's on each of the CH4s. That's a total of 8 H's. And so then we have 4 O's that are left, so we can make 4 water molecules. So 1, 2, 3, 4 in the case of the waters. That's 8 H's and 4 O's. So we can mix together really any proportion of reactants that we wish, and then we're just going to have them form as many products as are possible. It's possible, imagine we did this reaction with one extra CH4. So imagine we did this with 3 CH4 molecules. What would generally happen is that you'd just be left with an unreacted CH4 left over on that sort of, not really on the product side per se, but left over after the reaction completes itself. If you're thinking of a before and after, anything that's not consumed in a reaction would simply be left over as what we'd call an excess reactant. That's a term we'll pick up a little bit more as we get through the chapter. So let's talk about molecular weights for a minute. Substance is a molecule, and the formula weight's called the molecular weight. So we're talking about something like glucose, or the case of having all non-metallic elements. The only difference is if you're comparing with something like, say, NaCl, where this isn't a molecule, you might classify the formula weight of this particular formula. It not being a molecule, NaCl not existing as a molecule, kind of means we won't call or give NaCl a molecular weight. If we use anything, if we want to add up the atomic weight of sodium and chlorine, we would establish that as the formula weight for NaCl. So if we have a molecule, we could calculate the molecular weight. So we'll just do 6 times, let's do this a bit more neatly. So we would do the carbon for 6 times 12.01 AMU. I often get a question of how many sig figs you should use on masses. Well, you should use more than what you need given whatever the units are in your problem. I think if you get in the habit of using usually 2 digits for everything except hydrogen, throw an extra digit on hydrogen, then you'll always have enough. The key is you would just want to use enough digits on a molar mass so that in your given problem, you're not rounding your result prematurely. So if you have a really precise mass, you might need to look these up more precisely. On an exam in the class, not something that you'll be worried about. You know, usually if you just use 12, 1, and 16, you'd probably be fine. I usually use 12.01, 1.008, 16.00 is what oxygen rounds to 4 sig figs. But do this, and this ends up working out to be about 180.2, I believe. So let's do this math real quick. So 6 times 12.01 plus 12 times 1.008 plus 6 times 16.00, it's 180.16. So that means one molecule has a mass of 180 AMU, and that's per one single molecule. So one molecule in AMUs has the mass that we get using the periodic table. Okay, now for most problems this isn't necessarily going to be all that useful, because then if we want to go to grams, we have to convert AMU to grams. If we want to use moles, we'll talk about that in the next slide. We may need to make another conversion, but let's take a look at the next slide. Okay, so Avogadro's number simply defines a mole to be 6.02214.076 times 10 to the 23 objects. So a mole of anything is just this number. It's a huge number of that thing. So if we're talking atoms, a mole of carbon atoms would be 6.02214.076 times 10 to the 23 carbon atoms. Okay, now this is the definition of the mole now. So the mole is just defined as being this quantity. It used to be the case that we defined the mass of carbon-12 to be exactly 12 grams, and then from there you kind of define your mass scale. So this has just been kind of inverted. To say, well, let's treat this as the mole and then address how many grams each, the carbon atom weighs as a result of this. So let's take a look here. So there are 6.02214.076 times 10 to the 23 carbon-12 atoms within a sample of carbon-12. That's, approximately or exactly equal to 12 grams. So in the sample, this is in the sample of 12 grams of carbon-12. So if you have 12 grams of carbon-12 has an Avogadro's number of carbon-12 atoms. So if each atom has a mass of 12 grams exactly, or near exactly, divide by Avogadro's number, then that gives us, so if we do 12 divide by 6.02214.076 times 10 to the 23, if we do that arithmetic, that works out to be 1.9926, and we'll go ... You can write more down if you want, times 10 to the minus 23 grams. So in the AMU scale, the way this works out. So each of the carbon-12 atoms has this mass. So let's say, okay, so each carbon atom has a mass of 1.9926 times 10 to the minus 23 grams. So in the AMU scale, what we can do is say, well, what if we set 12 atomic mass units to be equal to this number of grams? So we're just saying, okay, we started with a mass of carbon that's 12 grams that contains an Avogadro's number of atoms. We use that to figure out the mass of each one of those atoms. We then say, well, what if we set 12 AMU to be equal to that particular mass? And then, so divide this number here by 12. So divide both sides by 12. So divide that 1.9926 times 10 to the 23 by 12. We get 1.66 053 times 10 to the minus 24 grams. Okay, this was the conversion that we gave you guys back in chapter 2 for the link between the gram scale and the AMU scale. So what we've essentially done is just said, okay, how many atoms of carbon-12 are there in an exact 12 gram sample? The answer is Avogadro's number of carbon-12 atoms are observed. So then we say, okay, well, let's work out the mass of one of the atoms in grams. Let's set 12 AMUs to that mass, and then let's define the AMU to mass conversion as just that simple conversion. And then, oh, by the way, like we showed earlier, 1 gram would be equal to, this should be AMU, in terms of AMU. So the 1 AMU is this small number of grams. 1 gram ends up being equal to 6.02214076 times 10 to the 23 AMU. So 1 gram is equal to an Avogadro's number of AMU, and then 1 mole is equal to an Avogadro's number of particles. Okay, so let's come back to glucose for a minute. So we have C6H12O6. We've had a formula mass of 180.16 AMU per molecule. Let's transfer that to grams per mole and say, how many grams per mole would that be for this particular molecule? So if I had a whole mole of glucose, if I had 6.02214076 times 10 to the 23 molecules of glucose, what would that mass be in grams? Well, I know it's 180.16 AMU per molecule. I know there's 6.022, I'll just go ... times 10 to the 23 molecules per mole. And then I know there's 6.022 ... times 10 to the 23 AMU per gram. So this Avogadro's number cancels out, and so then AMU molecule cancel out to grams per mole. So this would be equal to 180.16 grams per mole. Okay, so I'm sure like this is confusing, and we'll probably show this derivation in class in a similar approach. Maybe it'll sink in then, but it almost doesn't have to sink in, because all we're really trying to say is if you use the periodic table and the average atomic weights it lists to calculate a formula weight or a molecular weight, that tells you either the mass of one molecule but in the units of AMU, or the mass of a mole of the substance in grams. And we call that a molar mass. So we can, sort of look at this value here, the 180.16, this is our molar mass, because it's the mass of a mole of the substance in grams. And then we can look at this value here as being a molecular weight or a formula weight. For molecules, they're interchangeable. For ionic compounds, you would just call that the formula weight. So this is the idea that formula weights and molar masses go hand in hand with each other. They're very synonymous, very intentional, that we're choosing the conversion factor for AMU to grams to be the same as that conversion factor numerically as the molecules to mole conversion. Okay, so molar mass is the mass of 1 mole of a substance. Sodium, for example, has a formula weight 23.00 AMU. So now this means 1 atom of sodium on average weighs 23.00 AMU. And it also means that sodium has a molar mass of 23.00 grams per mole. So back when we were calculating average atomic weights, we were kind of taking, if you remember, the average atomic weight was the sum of over all the isotopes of the fraction of the isotope times the atomic weight of the given isotope, and adding these all up. And the thing that may have been strange back then is thinking that, a given atom, if it exists, say, as 2 isotopes, it's either one or the other. Well, when you have a mole of the sample, it's going to be the fraction that's the one isotope that amount of the time is going to be the fraction of the other isotope that other amount of the time. So when you're dealing with a mole of substances, if you say have a case where you have a 60%, it's one isotope, and 40% of the time it's some other isotope, say you have isotope A and B, then the having a mole would mean, well, 60% of that Avogadro's number of particles would be the one isotope, 40% would be the other isotope. So you get a greater appreciation for why you want an average atomic weight once you start dealing with larger quantities, like dealing with gram quantities, where we're picturing having these relatively large quantities in the order of 10 to the 23 particles. So we can convert from grams to moles of a substance using the molar mass. So if we say you have 15 grams of glucose, you can use the grams per mole to calculate the moles of glucose that are present. If you have less than the formula weight, then you have less than 1 mole. Then you can use Avogadro's number to calculate like the sort of the units that you have. So if you're talking about a molecule, you might say, well, how many molecules of glucose are there within this sample? And so we'd use Avogadro's number. You could also then go one further extent and say, well, how many carbon atoms are there in the sample? Or how many hydrogen atoms are there? How many oxygen atoms are there? How many total atoms are there? Because we have 24 total atoms per molecule. We have 6 carbon atoms per molecule, so you can do further conversions. So let's take a look here at 2 examples. How many copper atoms are in 3 grams of copper? Okay, so for this problem, we're going to need a periodic table. So I'm just going to my place of opening up that particular periodic table. So daily quizzes, if you need a quick periodic table, there's some sample info there. Okay, so I want to know a number of copper atoms. We'll use dimensional analysis. We have 3 grams of copper. I can use the mass listed on the periodic table, 63.546, but I need it down here. That's grams of copper per mole of copper. So 1 mole of copper has a mass of 63.546 grams. So I'm getting this from the periodic table. The average atomic weight of copper. And then I can use 1 mole of copper contains an Avogadro's number of copper atoms. So 6.022 times 10 to the 23, so 4 sig figs on Avogadro's number is good enough. So copper is comprised of copper atoms. So we have an Avogadro's number of copper atoms per mole of copper. Okay, so we do the arithmetic here. Much less than a mole. So 3 divided by 63.546. That would be 0.0472 moles. I'm going to multiply that by Avogadro's number, 6.022 times 10 to the 23. And I get 2.84 times 10 to the 22. Copper atoms. Okay, so that's using the molar mass and Avogadro's number to go from grams to moles and then moles to atoms. Now let's see how this varies when we have a formula. So we have methane here. So the number of H atoms in this sample would be equal to 1 gram that we're given. Now I need to calculate the formula weight, so I need to do 4 times 1.008 plus 12.01. That's 16.04 grams per mole of CH4. Now I can do this one of 2 different ways. I can go to molecules and then atoms, or I can think of how many moles of H there are for every 1 mole of CH4. Like there's 4 moles of hydrogen for every 1 mole of CH4. But I'm going to go to molecules first. I'm going to say 1 mole of CH4, which is a molecule, would contain an Avogadro's number of CH4 molecules. And then 1 CH4 molecule, each one of those molecules has 4 H atoms attached to it. So I'm doing 1 divided by 16.04. So that's about 0.0623 moles times 6.022 times 10 to the 23. That would be about 3.75 times 10 to the 22 CH4 molecules. And I got 4 H atoms on each of those. That takes me to 1.50 times 10 to the 23 H atoms. All right, so here's a quick example. So the empirical formula was found to be CH2O for a compound. Let's say its molar mass is 180.2. What is the molecular formula? Okay, so if we look at this unit here, it has a mass of 12.01 plus 1.008 times 2 plus 16. Now all we know is this is the empirical unit, so this is kind of like a formula weight. It's just the weight of this formula. We don't know if it's a molecule or what it is. We know the molecule weight, the molar mass of the molecule is 180.2. Okay, so we do this arithmetic here. This works out to be 12.01 plus 1.008 times 2 plus 16, because that to be 30.03 AMU. So the molecule could be, have 2 of these units, 3 of these units, 4 of these units. It turns out if we take the 180.2 divided by 30.3, that comes out to be 6. So the real formula here would be C6H2 times 6, O6. And you think of the C1 times 6. So you're just like taking all the coefficients, multiplying them by 6. So you end up with C6H12O6. Now notice that if you think of the percent by mass of CH2O or C6H12O6, they're going to have the exact same percent C, percent H, and the same percent by mass of O. So if you know this experimental information, then all you can do is calculate an empirical formula, and then maybe get additional information like a molar mass and be able to calculate the molecular formula. Maybe this stands out right now, but one of the topics in this chapter is going to be going from experimental data for things like percent composition or the mass composition of a compound. We can use that information to find an empirical formula for a substance and then do a second experiment that might furnish a molar mass, or have that as a second piece of information, and from that we can give and determine the molecular formula. Now, as we said before, the really important thing for a molecule is its molecular formula. That's really what we want to know, not really the empirical formula. So we'll see a 2-step process. We'll see some examples in class of going from percent composition by mass to an empirical formula, and then with additional data to the molecular formula. So another experiment that we'll talk about within chapter 3 is a combustion analysis experiment. What this experiment does is it takes a sample. Generally the sample is going to contain things like C, H, and O. Sometimes that third element is something else, maybe like N, S, Cl, some other element here. So sometimes this third element can really be anything. What goes on in the experiment is the sample is burned and produces CO2 and water. So all the carbon converts over to CO2, all the hydrogen converts over to water. So you can determine with this method, or what this method determines very accurately, is the mass of CO2 that's absorbed and the mass of water that's absorbed. And so that you can very easily determine the mass of carbon and hydrogen within the sample. So imagine you start with a sample that has some mass, and that mass contains your C, H, and your X. And then you determine the mass of C and the mass of H. That gives you the mass of X in the compound. And so then you basically have the mass of carbon, hydrogen, and that third element, and then you can determine from that an empirical formula. And then if you have additional information, perhaps from a mass spectrometry experiment like we talked in chapter 2, you might be able to get the molar mass, from which you can then get the molecular formula, together with the empirical formula you get from this combustion analysis data. So we'll do some examples of that in class and later in the course. So you can get quantitative information from a chemical reaction, like you could look at 2H2 plus O2 make 2 water. You can think of this in terms of molecules, 2 molecules of hydrogen combined with a molecule of oxygen to make 2 water molecules, like we talked about earlier, your before and your after in terms of what you have present before and after the reaction. You can also imagine that the coefficients could relate to the number of moles. So like let's say we take 2 moles of hydrogen, a mole of oxygen, we get 2 moles of water from that process. So the mass of 2 moles of hydrogen is about 4 grams, The mass of a mole of oxygen, about 32 grams. So 1 mole of hydrogen has a mass of about 1.0 times 2 for the 2 hydrogens. So 2 moles of H, mass of 4 grams. 1 mole of oxygen, a mole of O2, 32.0 grams per mole of O2. And then we're going to make from that 36.0 grams of oxygen. So our reactions balance. Notice we start with about 36 grams of reactants. We end with 36 grams of reactants. Now here's the most confusing aspect of this chapter when you first take a glance at it. We could mix together whatever concoction of hydrogen and oxygen that we want to mix together. I could take 5 grams of hydrogen, mix it with 32 grams of oxygen. What would happen? Well, we'll still end up forming 36 grams of water. We'll just have that 1.0 gram of H2 left over if it's present in excess. So one of the problems that we're going to see is a limiting reactant problem where we can mix together whatever ratios of reactants we want, and then we just have to then figure out which one's present in the excess amount, and then hence would just be left over after the reaction completes. So our coefficients in the reaction, those are relating the relative molecules of reactants and products, and those are also relating the relative number of moles of reactants and products. So 2 molecules of H2 combined with a molecule of O2 to make 2 molecules of water. We could also say that if you had 2 moles of H2, they would react with 1 mole of O2 to make 2 moles of water. That is to say 2 times Avogadro's number of H2 molecules, react with 1 times Avogadro's number of molecules of O2, you get 2 times Avogadro's number in the case of molecules of water. So here's an example of a stoichiometry problem. How many grams of water can be produced from the complete combustion of a gram of glucose? The combustion reaction is given in balance for us. Oddly, there is a small typo. This should be 6 CO2. So we're missing the carbon. So we're making 6 CO2 from oxygen reacting with glucose. So 6 carbons on both sides, 12 hydrogens on both sides, and then 6 plus 6 plus 12, should be 18, oh yeah, 18. So we get 12 here, plus the 6 here for 18 oxygens on both sides. Okay, so if we're trying to figure out the number of grams of water that can be produced here, we would take the gram of glucose times the molar mass of glucose. So we worked that out before. 180.16 grams are present for every 1 mole of C6H12O6. And then our coefficients say for every 1 mole of glucose that reacts, we produce 6 moles of water. And then we just use the molar mass of water. 1 mole of water is 1.008 times 2 plus 16.00. That's 18.02 grams. So this is just the molar mass of water. And if we work this out, so we do 1 divided by 180.16 times 6 times 18.02, we get a mass of 0.600 grams. So 0.6 grams of water forms from the combustion of 1 gram of glucose with an excess amount of oxygen. So again, coming back to the discussion of limiting versus excess reactants, you can mix together whatever concoction of reactants you wish. It's just if you don't mix together the perfect amount of your reactants, then one of them is going to be left over. We call that the excess reactant, the reactant that remains once the limiting reactant has been consumed. And the limiting reactant is the one present in the smallest stoichiometric amount. It's the one that's consumed in the reaction. So the smallest stoichiometric amount would be like thinking of H2 plus O2 goes to water, the 2 waters. The stoichiometric amounts is that we need 2 hydrogens for every 1 oxygen. So it's not necessarily the least present reactant, it's the one present in that least stoichiometric amount. Probably easiest to picture this with a picture. So let's imagine we have 10 hydrogens and 7 oxygens. Obviously 7 oxygens is the least present molecule, but it's stoichiometrically not the least present reactant. Let's take a look at lassoing out. So the red of the oxygens, I can tell because it's the one we have 7 of. 1, 2, 3, 4, 5, 6, 7. And then if I want to lasso out 2 hydrogens for every 1 oxygen, I can do that. So, and those are going to react to produce 1 water and then the other water. And so I might sort of say, okay, there's 2 of my waters being made. I do this again, lasso it out. So I get 2 more waters being made. And then I can do it again, lasso out the water. So there's 2 more waters being made. And then I can do it again. There's 2 more waters being made. And then finally I can do this one more time. And there's 2 more waters being made. And then I have 2 oxygens that are left over that are unreacted. And so they're left over once the reaction finishes. So this is my excess reactant. So the O2 here is the excess reactant. H2 is consumed, so H2 is my limiting reactant. H2, not H2O. H2 is the limiting reactant. It's when completely consumed in the reaction. So for 10 hydrogens to react, we need 5 O2s to react with them. And if we do, we're left with 2 O2s behind after the reaction completes. So we lose 10 H2, we're left behind with 2 oxygens. And then we're making 10 water molecules in the process. So oxygen's present in the least amount stoichiometrically, or excuse me, hydrogen's present stoichiometrically in the least amount. For 7 oxygens to fully react, we would need there to be 14 water molecules. So that's why we know oxygens are excess reactant, because for all of this to react, we would need 14 H2 molecules. We only have 10, so we can't consume all of the oxygen present in this given quantity. So like I said, we can mix together however many molecules of reactants we wish. It's just if we don't mix together the proper 2 to 1 amount of reactants, one of them will be left over following the completion of the reaction. So this slide here is discussing the theoretical yield. The theoretical yield is the maximum amount of product that we expect to be made. We calculate this quantity using the stoichiometric problem using all of the limiting reactant. So if we're discussing the problem where we have 10 H2 molecules plus 7 O2 molecules, what we might say is that when these mix together, our theoretical yield of water based on the reaction of 2 H2 plus O2 makes 2 waters would be 10 water molecules. So that this 10 water molecules, that this would be our theoretical yield. So that's the maximum yield of water we would expect. Now the actual yield is sometimes lower. It's lower, maybe there's a byproduct that's made, maybe there's a side reaction that occurs, maybe there's some experimental errors. Generally speaking, the true yield of a reaction can't go above 100%. Now you can imagine making some experimental mistakes, maybe accidentally having some other products added into the water mass that make it appear as if the yield goes above 100%. But the true yield of actual water and just the water molecule from this reaction, that maximum yield would be 100%. So the actual yield sometimes we find is lower than 100% due to these side reactions and errors that might occur within a reaction. Now the nature here is that a lot of reactions sometimes have a characteristic yield. So maybe some reactions will only yield 90% every time you run them, or some amount that becomes consistent if you were to repeat the experiment. So to find the percent yield, what we would do is take the actual yield, divide it by that theoretical yield, multiply by 100%. That would give us the percent yield. So very simple calculation. Now we could use the percent yield, maybe we'll find a percent yield for a problem. Let's say it's 85% yield. We can also do some problems that might say, well, how much reactant do you want to mix together to make so much product given the yield's 85%? We'll look at a few examples that involve that type of problem as we go through this chapter. So let's look at a couple problems here that kind of wrap up stoichiometry. So let's imagine we're taking 25 grams of hydrogen, or excuse me, 2.50 grams of H2, 25 grams of O2, fully reacting them together. Let's try to identify the limiting reactant, the excess reactant, how much of it remains, and then what the percent yield of the reaction is if 21.25 grams of water forms. So you might give a pause and give this problem a try. So you might begin with writing, here I'll go back to black ink. So let's go to writing the reaction. So 2H2 plus O2 goes to 2 waters. 2.50 grams, we might convert that to moles. So let's do that. I'm going to go 2.5 divided by 2.016. So I'm just converting this to moles, saying the number of moles of H2 would be equal to 2.50 grams times 1 times 2.016 grams per mole of H2. And so when we do that, that's 1.24 moles. And then if I do 25 divided by 32, that's 0.78 moles. So if I'm going to consume all of the oxygen, I need twice as much H2. I don't have that. If I multiply the oxygen moles by 2, let me throw in one more sig fig, that'd be 0.781 moles. But that's still well above the moles of hydrogen I have given. So the H2 is going to be my limiting reactant here, because I'm going to consume all the 1.24 moles of H2. Then for every 2 moles of H2 I consume, I'm going to lose 1 mole of O2. So the number of moles of O2 that should be consumed would be equal to the 1.24 moles of H2 that react, times for every 2 moles of H2, because there's a coefficient of 2 in front of H2, we need 1 mole of O2 to react with it. So we're just kind of saying, if you react this quantity of H2, how much O2 do you need to react with it? Well, 2 to 1, so we got to cut it in half. So 1.24 divided by 2, that's 0.62 moles of O2 react, leaving behind the excess of oxygen that remains. Okay, so H2 is fully consumed, that's our limiting reactant. How much of the excess reactant remains following the reaction? Well, in terms of moles, would be 0.781 initially is present, 0.62 is consumed, so 0.161 moles of O2 remains. 1 mole of O2 has a mass of 16 plus 16, 32.00 grams. That's 5.15 grams. Okay, so now if we think about it, we've reacted all but 5.15 grams of oxygen and 2.50 grams of H2. So in a way, like, since I'm only making one product here, I could take advantage of that and say, okay, I'm taking really 25 minus 5.15 grams of oxygen, that's 19.85. Adding that to the 2.5 grams of hydrogen, that should be a yield of 22.35 grams. Now I can check that. I could say, okay, well, how many grams of water do I expect to form when 2.50 grams of H2 fully reacts? And so then you can take, okay, there's 2.016 grams per mole of H2. For 2 moles of H2 that react, we form 2 moles of water. 1 mole of water has a mass of 18.02 grams, just the molar mass of water. And so if we work that out, let's see if this checks out. 2.5 divided by 2.016 times 2 divided by 2 times 18.02 works out to 22.35. So it does check out. So we got a quick little check. Now you can't do this on all problems. If you have 2 products, it's not going to work out so simply. But in the case of having one product, we can use that to our advantage on a problem like this, or double check our yield calculation to make sure everything's in check. Now, one other thing you can do, in some ways of solving and determining the limiting reactant, go by, well, just figure out how much water would be made if you consume all of the oxygen. So imagine you take the oxygen, 25.0 grams, of O2, and fully react all of it. So that's 32.0 grams per mole of O2. Now for every 1 mole of O2 that's consumed, we still make 2 moles of water. So it's just 1 to 2 for O2 to water. And then 1 mole of water is still 18.02 grams. So let's see what happens and then explain it afterwards. 25 divided by 32 times 2 times 18.02 gives me 28.16 grams. Now, at that point, what we can see is that if I consume all the hydrogen, I make 22 and some odd grams of water. If I consume all the oxygen, I would make 28 grams of water. So I must need more hydrogen than what I have available to make 28 grams of water, so that must be impossible. In fact, I only have 27.5 total grams of reactants available. I can't create a mass through the problem here, and I have to follow the stoichiometry of the reaction. I have to follow the 2 moles of hydrogen react for every 1 mole of oxygen to make 2 moles of water. I have to follow those coefficients. So the max yield is 22.35. So the percent yield would be the actual yield, 21.25, it says, divide by the theoretical yield calculated of 22.35 grams times 100%. It's going to be a pretty good yield, pretty high. That is 95.08% yield. So a pretty high yielding reaction in this example. Okay, that's just a sample stoichiometry problem. Now if you're seeing that and it doesn't make total sense, we'll of course look at examples in class. We'll see some more examples in a later summary video, and hopefully this just gets you a start of really the types of problems you're going to see in Chapter 3. That's all for this video. Thanks for the attention.